So in this lecture, we'll talk about classification of mechanisms. And you might say, well, why do I want to classify a mechanism? Well, one, it just helps us improve our communication so we can be able to say, yes, I understand what you're talking about, but also allows us to figure out how do we want to synthesize the mechanism, or how do we want it to move, and so on and so forth. So for example, the trash can that you see on the slide there, that happens to be a 4-bar mechanism, or you can imagine I push down with my foot on that pedal right here. It pivots about this point right here on the trash can. It causes this point to go up. That then pushes up this link right here, which then flips the lid, which is pivoting on the back there. So it happens to be a 4-bar mechanism. It also happens to be a function generator in that I have an input that is a rotation driving a rotation of an output. So I'm creating a function between rotation here and rotation here. And it also happens to be a rocker crank mechanism in that my input link rocks, and if I allowed it to go far enough, my output link would crank. So we'll talk about all those different classifications and look at 3 different ways to classify mechanisms in this lecture. So as I mentioned, 3 classifications we are considering. First of all is the task classification. What's the purpose of the mechanism? So in other words, the first trash can that I was talking about, that happened to be a function generator. That's the task of it. Then what's the range of motion? How can it move? The crank rocker, rocker crank type of description. And then finally, what is the type or the link set? How many links are there? How are they arranged? And with all of these, we can then describe quite a bit about a mechanism. And there's also other classifications we could apply as well, but we'll stick with these for now. So our task classification is important from the standpoint of thinking about how am I going to synthesize my mechanism. So I have 3 different tasks that I'm going to be interested in: function, path, and motion. But before I get there, I need to look at this 4-bar on the right and define some of these links and the link lengths in terms of variables that I'll be using for my synthesis. So what I'm going to use here is, starting off on the ground pivot of the input side of the mechanism, I'm going to have a vector from the ground pivot up to the moving pivot, and I'll call this vector the W vector. And then going from that moving pivot up to the coupler point, which is really the location of interest for both path generation and motion generation, I'm going to have what we call the Z vector. So we call this the W and Z side of the mechanism, or the input side of the mechanism. Now, not very creatively, we have for the output side of the mechanism the W star and the Z star vectors. So going from the ground pivot on the output side up to that moving pivot, I've got the W star vector. And similarly, from that moving pivot up to the coupler point, make that a little thicker, I've got the Z star vector. So those are the vectors that I'm going to use to describe the length between the individual pivots. Now I also need to describe their rotations. And the way I do this is with rotation angles. And the rotation of the W vector, this is going to rotate by an angle beta. Typically call it beta 2, first to the second position, beta 3, first to the third position, and so on. The coupler, which includes both the Z vector and the Z star vector, this will rotate by some angle that we'll call alpha. So that's the entire coupler is going to rotate by alpha. And the W star vector rotates by an angle that we typically call psi. So that then describes enough for me to synthesize a mechanism. So now let's move back to those tasks that I was talking about. First of all, in function generation, what we're doing here is we are coordinating motion between an input and an output link. These are the links that are pinned to ground. So when I was looking at the trash can mechanism in the first slide, there I was coordinating rotation of the input link, the link that was pinned to the trash can that I pushed on with my foot, relative to the lid of the trash can, which is also pivoting on ground, and input-output links coordinating their rotations. That is a function generator. And if I describe this in terms of the variables that I just used for this 4-bar mechanism, I can now say, well, what are those terms? I am going to be prescribing, or having come as part of the problem statement, both rotations. So I'll be prescribing the rotation of the input link, beta, and I'll likely have multiple rotations, so betas, and I'll be prescribing the rotation of the output link, the psi angles, so psis. So that is what I prescribe in a function generator mechanism. Now let me move on to path generation as our second task. In path generation, I'm prescribing or controlling the movement of a point moving through a path in space. Now, This mechanism right here happens to be a path generator. And you'll say, well, first of all, what is this thing? What this is this is an oil pump rig. Now, if you head out to western North Dakota or Texas, you'll see lots of what they call a horsehead type oil pumps, so they're moving a large piece back and forth with then kind of an arced head and moving a cable up and down, or sometimes a rigid link up and down in the ground. Well, those are quite bulky. This is a more compact design of that same thing, where I'm able to create very close to a straight line motion, which is needed because I'm moving right above this vertical well. And as I rotate this, you'll see I move almost in a straight line motion up and down above that well location. Now, because I have a pivot right here, I really don't care what the orientation of my coupler is, which is this component right here. I don't care about the orientation of my coupler point. So I really don't care what the alpha rotation angles are. So this happens to be a path generator where I'm controlling this point moving through space, or a point along a path. So that is a path generator. And in path generation, what we're doing is we are prescribing the motion of the coupler point. I need another vector to describe that. And so as I go from a coupler point I might call P1 to another point which I might call P2, I then have a displacement vector from point 1 to point 2, and I call that my delta vector. And so I can go delta 2, point 1 to 2, delta 3, from 1 to 3, and so on. So what I'm prescribing here in motion generation is I'm prescribing the displacement vector delta, and typically deltas. Finally, getting to motion generation. Now, motion generation, we're controlling not only a point, but also its rotation. So we talk about it as describing a body moving through space. Or in other words, the entire coupler, not only its location, but how much does it rotate. Now, an example of that happens to be this mechanism over here, which is a golf tee resetter. So imagine that I have a large number of golf balls queued up in here, and now this mechanism comes in, grabs the golf ball out of the nest, brings it over, sets it on the tee, and then you can hit it, and then it'll come back and grab the next one. Now, if I did not care about the orientation of this part of my coupler, then the golf ball would fall out of this nest as I was moving it from, or the gripper as I was moving it from the nest to the tee. We don't want that to happen. So we are controlling not only the point or the path that this moves through space, but we're also controlling its orientation. So this is a motion generation problem. And in this case, what we are prescribing is both that displacement vector. So we're prescribing the displacement vector that we did in path generation, or the delta vector. And we're also prescribing the rotation of the coupler, which is the alpha angles. So that is how we think about these three different tasks in terms of what do they need to do, as well as what variables do we use to describe those, because this will then come into how do we synthesize the mechanism for these individual variables that are prescribed. So we need to know what its task is before we can get to actually starting to synthesize it. All right, let's move on to range of motion. So in a range of motion classification, I'm interested in how does the mechanism move. And you'll look at what I have sketched here for a simple 4-bar. I've got an input link, which if I started rotating it, you can imagine that, okay, yeah, it would make a complete revolution and kind of follow that moving pivot right there would follow that circular arc. Well, we happen to call this a crank because it makes complete revolutions. And as it does so, what would happen to the output link? Well, because of the geometry of this, my output link would move back and forth in an arc, and we call this a rocker. So because my input side of the mechanism is a crank, the output is a rocker, I call this a crank-rocker mechanism. And that is enough to describe generally how does this mechanism move. Input cranks, output rocks back and forth. Now, if I happen to flip what the input and the output were, in other words, if I was grabbing onto that output link, the longer link, and driving that back and forth, now I would have a rocker crank because the rocker would be input, the output would then be the crank. So again, based on what is the input, what's the output, that's how we describe rocker crank, crank rocker, and so on. Now, we want to know more generally, when do we have one link that makes complete revolutions? Now, what I've shown here in a crank rocker is one of those types of mechanisms. And the reason we would want that is because then we can drive this with an electric motor. So something like the oil pumping rig, I want to have an electric motor that's driving this again and again to actually be doing the pumping of my oil. Well, I need to know that this is going to be what we call a Grashof mechanism, which is a mechanism that has one link that makes complete revolutions. So we have what we call the Grashof condition, which is just this inequality of this S plus L being less than or equal to P plus Q. And if that's the case, then I have continuous rotation between two links. Okay, great. Continuous rotation that allows me to put a motor between them. But what is S, L, P, and Q? Well, these are simply the length of links in our mechanism. So S happens to be the shortest link length. L happens to be the longest link length. So I'm going to take those two, I'm going to measure how long they are, add them up. And if that is less than the length of the other two links, the P and the Q link, then I happen to have a Grashof mechanism where I'm going to have complete revolution between one link relative to another. This guy right here happens to be a Grashof mechanism, where my longest link is the green link, the shortest link is the black link. The other two links, the gold and the silver, those are greater than S plus L. So S plus L, that's this entire length right here when I got them straightened out. That is less than P plus Q. Therefore, this is a Grashof mechanism. And if I grab this guy, I see I can make complete revolutions of it, and I have a crank rocker mechanism. Or if I drove this one over here, I would have a rocker crank mechanism. So this happens to be a Grashof mechanism. Well, let's start looking at that in a little bit more detail. So let me kind of break this chart down into a kind of a build, if you will. Let me first of all look at this S plus L being less than P plus Q, this mechanism I have right here. This is a Grashof mechanism. And you'll note that I have different kinematic inversions based on where I am putting my ground pivots. So in the first case right here, I've got a ground pivot here and here, and my shortest link is the input. Then I move to here, and my shortest link is ground. I move over here, and now my shortest link is the output link. And I move over here, and my shortest link is the coupler link. Now you'll notice that I'm talking about where the shortest link is, because that actually determines how our mechanism is going to move. So if our shortest link is if short link is the input, then we are going to have what we call a crank rocker mechanism. And that's what I was just showing a moment ago, where this black link happens to be the shortest one. If it's my input, then I have a crank rocker mechanism. Now, if I take that next inversion and say, let me make the shortest link ground, and then look at how everything else moves relative to that, if I can do that without pinching my fingers, you'll see that the entire rest of the mechanism, or the blue and the silver, the other ones that are pinned to ground, the input-output link, those make complete revolutions. So we call that a crank-crank mechanism. And so if the shortest link is the ground link, then we have a crank-crank mechanism. If I move to that next inversion where I have, in that case, my shortest link is the output link. In that case, I have a rocker crank. So I'm driving this gold link as my input link. The black one is my output link. I have a rocker crank. And that's because my shortest is the output. And finally, I can then move to the point where my shortest link is the coupler itself. And you might say, well, wait a minute. Both my input link and my output link no longer rotate back and forth. They only rock back and forth. Why is this a Grashof mechanism? Well, you'll notice my continuous revolution is now up at the coupler. And I could, if I wanted to, place a motor between these two links. And this is still a Grashof mechanism, and we call this a Grashof rocker-rocker. So my shortest link is the coupler, and in this case, I have a rocker-rocker, a Grashof rocker-rocker. All right, so that's when S plus L is less than P plus Q. What happens when they are equal? Well, we call these change point mechanisms. And this would be a parallelogram mechanism or something like a deltoid. But what happens is that all the links at some point become collinear. They're all in a line. And as you come out of that condition, it's unpredictable because you can branch in two different directions and its motion is really unknown. But you have some very interesting behavior from parallelograms. You can keep the coupler parallel to the ground all the time through the range of motion. Or a deltoid or a Galloway mechanism have some very interesting behaviors. A Galloway mechanism, you actually have two rotations of the input link for one rotation of the output link. Also, there are further divisions of this that Barker further classifies that we're not going to spend much time on, but recognize we can take this and further classify these change point mechanisms, S plus L is equal to P plus Q, beyond what I'm showing here. Now, What happens if it's not a Grashof mechanism? So those first two categories, those are Grashof mechanisms. Now this right column, these are non-Grashof mechanisms. And in this case, no link makes a continuous revolution with respect to the others. So I can no longer put an electric motor on this and drive it through continuous revolutions. In other words, I have to oscillate a link back and forth. And these are called triple rocker mechanisms. They're just as valid, they work just as well, but if we want to drive it with an electric motor, this would not work directly. Instead, we have to add something else to drive the mechanism through its range of motion. So knowing its range of motion really helps us determine how is it going to move and can I apply a motor to drive this through its range of motion or not. So we've talked about two different classifications. Let's now move into the third one, the type or the link set classification. Now we've already talked about a group of these with the 4-bar mechanisms where we were looking at the Grashof or the Barker classification, which further subdivides the Grashof and the triple rocker mechanisms. We looked at those, but we also have many other 4-bar mechanisms. Another category are crank slider mechanisms or slider crank mechanisms. Now, where you very commonly see these are in internal combustion engines where you have the crankshaft driving a piston, or actually the reverse, the piston driving the crankshaft to create power. In an air compressor, you have the crankshaft driving a piston, but a lot of other places where you have a slider and a crank being driven relative to each other. This is the common kinematic inversion, but recognize that I can create 3 other kinematic inversions of these as well, tumbling block, turning block mechanisms, which are simply changing what is ground in this mechanism. So it does not have to be that the slider is moving on ground. The slider can be in space. The slider can be having a pivot on its center and be rotating about its center point in the turning block mechanism. Lots of inversions that we can look at and create some very interesting mechanisms. Now, we also have another class of 4-bar mechanisms, which we call the double sliders, where we have 2 sliders, in this case moving on ground, but you can imagine I can have other kinematic inversions of those. So these are really the 4-bar mechanisms or the 4-bar link sets that we have. What if I want to get more complex than what a 4-bar mechanism can do? Well, the next idea is let's add another link, and we jump up to a 5-bar mechanism. Now, if we applied the Grubler's equation to a 5-bar linkage, we'd find that it has 2 degrees of freedom. So this means I have to have 2 inputs to completely control where it is in space. Now, in some cases, that might be good in that I would have 2 inputs and I could control its location very accurately and with more than a single degree of freedom. But very often, we only want to have a single input to a mechanism. So how can I take this 5-bar and reduce it down to a single degree of freedom? What I can do is I can add a gear pair, and I can really add it between any links. Here I'm going to show it between ground and that first coupler link, what we normally refer to as link 3. So you can see that as I would rotate my input link, as I would take this guy right here and rotate it, now this gear right here is going to roll on this gear, and then we'll be coupling those 2 degrees of freedom and removing an extra degree of freedom. So now I only have 1 input to this geared 5-bar. And this, where you often see these is if I call this rotation maybe theta 2, and the rotation of this side over here, theta 5, so I have link 1, 2, 3, and sorry, where'd I go? I missed 2. So link 1, and then link 2 right here, 3, 4, and 5. If I'm looking at theta 2 relative to theta 5, very often I want to create what we call a dwell mechanism. So if I look at theta 2 as a function of theta 5 or vice versa, perhaps I want to have some sort of a rotation and then hit a flat area where theta 2 keeps rotating and then it does something like this. Well, this section right here we call a dwell, and these geared 5-bars are very good at being a dwell mechanism where the input link keeps rotating, the output link really stays close to stationary. So we can come very close to a dwell with these geared 5-bars. Now, very often we jump straight from a 4-bar all the way up to a 6-bar mechanism because these then become single degree of freedom. Now, there are 8 unique isomers of 6-bars. But as we start to look at how are the degrees of freedom distributed, we find that only 2 of these 8 isomers are useful. And the 2 useful isomers are the Stevenson and the Watt chains. And both of these have a single degree of freedom, and we can create multiple kinematic inversions of these based on which link we hold as ground. and actually create 5 different mechanisms from these 2 isomers. So a lot of capability with these 6-bar mechanisms. You can imagine that I can replace individuals links of these with sliders and so on. So I can add a lot of complexity, but this is really just scratching the surface and finishing up this type and link set classification. So we've talked about 3 different classifications. First of all, what is its purpose? What's its task? And anything from a path generator to a motion generator or a function generator. Then talked about what's its range of motion. And here we use the Grashof condition to describe the range of motion of 4 bars. And then moved into type and link set. And here we have 4 bars with all the inversions as we add sliders to them. And going into 5 bars, geared 5 bars, 6 bars, we can move into 8 bars and more complex mechanisms. So this just gives us a way to talk about mechanisms in a common terminology with these classifications.